Hi everybody. Today I'm presenting our TUM EDGAR autonomous driving research platform, from feature development to real-world application. We at TUM sat down and looked at current autonomous driving problems today which are unsolved. Firstly, we see there's a lot of issues with uncertainty. We see uncertainty in perception, for example, occluded cars or pedestrians. We see uncertainty in planning, for example, when it comes to interactions. And we see uncertainty in control when it comes to model mismatches. Number two, we see a lot of complexity. In unstructured environments, for example, as you see in this video here, we have high prediction uncertainty where we also need to plan complex interaction with others. And number three, safety is a big issue. Our vehicle needs to behave safe and reliable all the time, especially in emergency situations. And in order to have a secure and validated algorithm, we need safety confirmations. Based on this, we discussed what do we need. We want to have the possibility of developing new algorithms for autonomous driving and use existing ones that can cooperate in a full autonomous driving software stack. Number two, we want to evaluate algorithms based on the performance and sensitivity in order to improve algorithms based on system knowledge. Number three, we want to have the ability to demonstrate real-world performances of algorithms, especially when it comes to real-time evaluation on high-performance hardware. Number four, we want to show how we can move algorithms from the simulation land into reality in order to bridge the sim-to-real gap. And number five, based on real-world testing, we want to extract new research topics. Based on this idea, we submitted a proposal to the DFG, Deutsche Forschungsgemeinschaft, for a major vehicle instrument. This project was funded by DFG, and we were able to now have our TUM EDGAR autonomous driving research platform. This vehicle is based on a T7 Volkswagen Multivan e-hybrid car and was specifically remodeled for autonomous driving. Well, you can see here that this vehicle is now equipped with new sensors. Then, number two, has access to steering, velocity control, and braking via CAN bus gateway. And finally, this vehicle offers us now a high dynamic driving mode for autonomous driving up to 200 kilometers an hour. This allows us now full stack autonomous driving testing on public roads, where we can evaluate our algorithms on real vehicle hardware, and it allows for data collection and new scenario generation. Firstly, you can see here the sensor setup of EDGAR. It includes microphones for collecting audio data, radar from Continental for long-range detection, two LiDAR setups for long-range and mid-range detection, an Auster 360-degree LiDAR, and an InnoVusion solid-state LiDAR. It includes long and short-range cameras, a multi-input, multi-output antenna for Wi-Fi and 5G, and a GNSS antenna for differential GPS from Novatel. You can see here the sensor setup, including the long and short range cameras, as well as the solid state and 360-degree LiDARs. Secondly, the vehicle is equipped with high performance computation platforms. We integrated two platforms. First, an ARM AVA AP1 platform, and second, an x86 Mayflower computer. This allows us not only to evaluate our algorithms in a whole car setup, but also for specific computation hardware. Both computers are connected to a network setup that allows us to also connect the sensors and a PTP clock for time synchronization. You can see here the whole vehicle, including the sensor setup and vehicle layout, in one of our research facilities. Here at TUM, we now started to develop and created testing environment. First of all, we develop autonomous driving software features. Those can range from perception, planning, and control. We are cooperating with the Autoware Foundation, where Autoware Universe is our core software stack for autonomous driving. We use and enhance Autoware with our own algorithms to create new perception, prediction, planning, and control algorithms. Everything we do is running in C++ and is using ROS2 as a main middleware. We containerized everything with Docker, so it's easy to port our algorithms to other setups. When we develop new algorithms, first of all, we test in software in the loop in 2D environments. And 2D environment that we heavily used is TUM Common Road from our colleague Matthias Althoff. This is a composable 2D scenario benchmark with over 15,000 testing scenarios that allows us to create new scenarios with a specific tool generator, allows us for basic software tests and planning and prediction, and allows us to develop our new trajectory planner. When we are done with the software in the loop testing, we are moving on to the hardware in the loop testing. Here, we replicated all the hardware that is in EDGAR already in a new setup, which allows us additionally for running 3D environments with a specific GPU server, simulate and visualize 3D environments with an visualization server, and additionally allow for real-time computing of the vehicle dynamics. Here, we can now do some full software stack testing with real computation hardware because it's replicated from EDGAR. And further, we are able to test in 3D environments. We heavily rely on EDGAR, but further also allow for AWSim. This open source simulator for 3D urban scenarios allows us now to simulate traffic, develop our comprehensive soft sensor models, and allow us for the development of new perception algorithms. We further created a 3D digital twin of EDGAR, which has an accurate sensor setup and sensor models, a 3D model of the vehicle, and finally, vehicle dynamics models with accurate parameterization. You can download and use the 3D model of EDGAR today from our GitHub website. You see here now our TUM EDGAR running in a 3D environment of Kala. This is a setup you can download today and drive with EDGAR in your own environment. Further, you see here how we simulate together with Autoware and in the AWS visualization in our Kala environment. You can see here our car is driving fully autonomously in this Kala setup. And if you're interested, you can use the setup and try it out on your own. Finally, after we are done with simulating, we move our software to EDGAR. We have the possibility of real-world testing because we have access to first a test center of intelligent mobility, thanks to our colleague Klaus Bogenberger. We are running the car on the TUM campus in Garching in suburban environments, where it's located at the Institute of Automotive Technology and our colleague Markus Lienkamp. And finally, since the car is street legal, we are allowed to drive in urban environments in the city of Munich. The car has some safety assessments, is TÜV approved, and we are allowed to drive autonomously with the safety driver on public roads. Finally, when we are done with the testing, all our data is saved on a data center, which was also funded by the DFG. We close the loop, create new 3D environments and 2D environments, and ultimately we will open source a lot of the code. Here's a special thanks to the DFG Deutsche Forschungsgemeinschaft who funded this vehicle and the data center, and a big thanks to all the professors who are cooperating in this project, ranging from traffic engineering and control, embedded systems and IoT, connected mobility, network architectures, decentralized systems, to the colleagues in computer vision and AI, dynamic vision learning, visual computing, and the colleagues from cyber physical systems, automotive technology, and autonomous vehicle systems. If you're interested to read more about the vehicle, you can download our paper, access our GitHub code, and if you want to work together, we are looking forward that you reach out to us. Thanks for your attention.